Hi, everybody. My name is Arsh, and I'll be your presenter today for data structures and algorithms. Unfortunately, it looks like everybody's not here, so we're gonna wait 3 minutes. And also, can you let me know in the chat if you guys can actually hear me? I just want to make sure. All right, hi, everybody. So it's been 3 minutes, and I think we have everybody inside. So now to start the presentation. So my name is Arsh, and I'm here to teach you data structures and algorithms. And this is only a beginner's guide. There's obviously a lot more to it, but this covers the most important things. All right, let's start. So table of contents. So first we're going to talk um, about me. So my background in computer science and why I'm presenting this, and then what are data structures, what is their importance, and then big O notation. Next, we're going to talk about linear data structures, nonlinear data structures, algorithms, and if we have time, we can do some exercises. So about me. So who exactly am I? Now this is going to be a little bit short, but I'm an incoming CS major at Purdue University. I have 6 years of coding experience, and I'm also the CIO and co-founder of High School Navigator. So CIO is Chief Information Officer. And if you want to see the rankings for Purdue, it's over here. So 18th best CS school overall. But that just means I know what I'm doing. So what exactly are data structures? So data structures refers to a system where information is collected and stored. So these data structures have well-defined operations called methods and behaviors. So an example of that could be a data structure could be a phone book because a phone book has names and phone numbers. And um, it actually kind of connects to one of the data structures we're going to talk about later, where they have keys and values. So a key could be your name, and a value could be your phone number. Anyways, it's just a system that holds information, and it does it in a structured way. So importance. Why do I need to learn data structures? There are three main things to consider when you're running a program: processing speed, searching data, and multiple requests. The benefit of certain data structures is that they're faster for processing. So if you need to find something or delete something, some data structures are actually better at doing that. Now, for searching data, it's the same thing. Finding and deleting certain things, some data structures are actually faster and take up less space. And multiple requests. Um, Now, when you have this data in the server, right, and you have people trying to get that data, it can actually use a lot of data, and that could crash the server. I mean, it gives a lot of memory, and that could cause a lot of problems. So, but why do I mention all these problems? Because they're important problems to consider when choosing a data structure. Some of them can be solved by using the correct data structure and finding out how exactly you want to store your data. And advantages of certain data structures are efficiency. Some are a lot faster at finding certain things. Some are a lot faster at deleting certain things, and they also use a lot less memory. And memory is important because it can also slow down your programs if it uses too much memory. Another important thing is reusability. Say you're going to parse a large amount of data, right? Um, I used the phone book example, but maybe if we had like sports teams, right? If you wanted to parse in all their scores for the seasons, right? Instead of having one data structure for each team, like the Los Angeles Lakers and the Boston Celtics, we could just have one, and then we could parse in each one of those things. And then when we are done with that, we could clear it, and that would use a lot less code, and it would make our program compile faster, and it'd use less memory, and overall it'd be more efficient. Another important thing is abstraction. So the Java ADT, which is what I'm teaching you right now, um, allows for a level of abstraction where you don't have to worry about what's going on behind the scenes. You just have to input or delete certain things. So an example of abstraction is imagine you have a car, right? Now you don't know how the car exactly works, but you know that you press the gas pedal, that it goes forward. And you press the brake, it slows down. Data structures are kind of the same thing. You know how to put something in, you know how to take something out, but you don't know how exactly the code works because you don't have to write it. And that's beneficial because it saves you time. Um, Important, actually, one more important thing about why it's so important is that data structures actually, it's kind of one of the questions they ask you while you're interviewing for companies, right? So if you want to, get into these big tech companies, you should have a high level understanding of data structures. Another important thing is big O notation. So a big OTT is a system that is used to measure how long an algorithm takes to run and how much space it uses, which is known as memory in the computer. And an algorithm is a procedure for solving a problem or performing a computation. So an example of an algorithm could be accessing something, searching something, inserting something, deleting something. And just so you know how it looks, here are a list of values for the very common data structures. So here we have the array, the stack, the queue, and the linked list. So what exactly do the big O values mean? The first one is O1. Now O1 means that there's a constant time to find the required information in the set. So imagine you have um, a list of groceries, and that grocery list doesn't change at all. It's always four values, right? And the second item in your list is milk, right? Now, if we wanted to find milk again and again and again, it takes the exact same time because it's always the same. It's always in the same spot. It's always the second item, and obviously the list doesn't change. It's always four. It's always the size. It's always four items. ON means that the amount of time it takes to find the required information is linear with the size of the set. So say we have something that like a list that grows bigger and bigger and bigger, and we have our item milk somewhere in there, right? And we keep adding these items to the end and the end of the list, right? Then it takes even longer to find the item because the size keeps growing and growing and growing, and we need to check all those items to make sure that they are not milk or they are milk. O log n means that the amount of time it takes to find the required information goes up linearly, while the quantity of information goes up exponentially. So obviously, if we go back, that could be, well, it wasn't here, but it was for actually the nonlinear data structures where that happened. So some example cases to help you understand what this actually means. We have O1, and so given the page that a business name is on and the business name, find the phone number. So the data structure that we're using is actually the phone book, right? And now that we know the page, right, the page has a constant amount of phone numbers, and we know where they are now, so it'll always be the same amount of time to find them. The next case is given the page that person's name is on and their name. So apologies. This is actually oh wait, no, this is different. And this is in the average case, right? So usually we use big rotation. It's in the worst case possible. So if nothing went wrong, that's what would happen. But for in the average case, this could also be the same. An example of O log n, given a person's name, find the phone number by picking a random point about halfway through the part of the book you haven't searched yet, then checking to see whether the person's name is at that point, then repeat the process about halfway to the part of the book where the person's name lies. This is actually a binary search for a person's name. And what essentially is going on is that they're actually kind of breaking apart the data structures into less and less data to find whatever we're looking for. And that kind of takes less time. And now we have an example of ON. I only use one of the examples because we're kind of a little bit behind, but find all the people whose phone numbers contain the digit 5. Now, obviously, as the phone book gets bigger and bigger and bigger, now we have more people who have the phone that contain the digit 5 in their phone number, and that's why it's ON, because it varies with the size of the data structure or the amount of information. So big O tells you the complexity of algorithms in terms of the size of its inputs. Size of the inputs is basically how much information you're putting in. This is important because it'll tell you how well your data structure will scale when you use certain algorithms. And by scaling, I mean when you use more and more data. This is important because we design different data structures for different functions, and certain data structures are faster and take up less time when doing certain tasks. All right, so the first one we're going to talk about is linear data structures. That means a data structure where all the elements are arranged in linear and sequential order. That means they're arranged in the order that you put them in, as opposed to being arranged randomly. So the first one and the most important one is the array. An array can be defined by a collection of some type. So you could have integers in there, floats, booleans. Booleans are true or false. And an important thing to note is that an array is actually a fixed size static data structure, which means you cannot change the size of the data structure. It's always going to be 3 items, 5 items, 6 items, anything like that. And another important thing to note is that all elements in the array, which are elements are basically items, right, are identified by the same variable name. So but what that means is only that there can only be ints in an array. No ints, booleans, and floats together, only ints. And an array can be one-dimensional, two-dimensional, or multi-dimensional. So one-dimensional is like just this line here, but two-dimensional is this line here and this line here. And what that means is you can have rows and columns of data. So basically a table. So here are some important functions: accessing and changing. So you can access an element by referring to an element's index. So we have here, we've created our array called cars, right? And we've put in Volvo, BMW, Ford, and Mazda. Now I want to access the 0th element. So just so you know, actually, one important thing, how numbering works in arrays is that the first element is called 0, second element is 1, third element is 2, fourth element is 3. So 0, 1, 2, 3. So if we run this piece of code here, cars 0 will get Volvo back. Now to change it, we have to kind of do the exact same thing. We have to access it and then we have to change it ourselves by saying it equal to something else, right? So now we're saying it to Opel. So now our array will look like Opel, BMW, Ford, and Mazda. So here is some example code. Now this over here is a method, right? And that's not really what we're focusing on right now. We're focusing on the driver code. So when your computer reads the code, it looks like this. So the first thing that's happening right now is that it's creating an array with these numbers inside of it, and then it's getting a integer value, a number, with how long the array is. And essentially what this code is doing is it's trying to find the value 40. And what's going on right now is we're parsing in these values. So we have the array, the number the size of the array, and the number it wants to find, and we're putting it inside of this method. Now this method runs, and it'll tell us if the value is there. So if it returns -1, it means the value is not there. If it returns I, it means the value is there. And this code will run, and it'll say the position it was found. And you'll notice that it says +1. As I was telling you before, elements are numbered 0, 1, 2, 3, but that kind of confuses people, right? So instead of doing 0, 1, 2, 3, we add 1 to the value, and it becomes 1, 2, and 3. So here's the big notation for arrays. And you can see that this is access, search, insertion, and deletion. And then here's the same thing for space complexity. Now we're only going to be focusing on time complexity because that's obviously our programs don't have lots of data. You can use up memory. So obviously, as I was saying, accessing, right? Arrays are static; they don't increase in size, so it always takes the same amount of time to find an element. Now, searching, insertion, deletion, those change. Moving on to the next data structure, we have the linked list. So a linked list maintains a list in memory into a collection of elements called nodes. So here is a node, here's another node, and here's another node. So this is actually a dynamic data structure, which means it can increase in size, and it has a head node and a tail node, and each available node is in a linked list contains a pointer to a different node. So you can see here this node right here, it has a point. This node called A has a pointer to node B, which has a pointer to node C, and likewise, if you go backwards, node C has a pointer to node B has a pointer to node A, and that's why they are different than arrays, because the elements of arrays are not actually connected. So some important methods are add, which obviously adds an element to the end of the list, get, which gets a certain element but does not take it away or delete it, set, which sets a certain element to a certain value, clear, which removes all the elements from the list, peek, which retrieves but does not remove the head or the first element of the list, and pull, which retrieves and removes the head of the list. Pop basically takes out an element from the stack represented by the list. So if you have like with those tennis ball stacks, right? Pop would be basically just taking out the first tennis ball. Contains, obviously that's just seeing if the list contains a certain element, and remove, which removes a certain element from the list. Now, so here we have some example code. So what we're doing here is we're instantiating or creating the linked list call languages, and now we're going to add elements, Python, Java, JavaScript, and we're going to print out linked lists plus languages. Now you might ask, what is that going to look like? What it'll look like, it'll have parentheses, Python, Java, JavaScript, and that's what it'll look like when you print it out. Now, this line of code over here demonstrates the get method. So language is if you wanted to get one, right? And it kind of works the same way, where it's numbered 0, 1, 2. So doing get 1 would get Java. And system out print an element index 1 string, obviously that's just printing out this. Now here are the time and space complexity big O notation for time a linked list. So the first 4 ones are the ones that matter because this is the one that deals with time. So for accessing, it's ON, insertion it's ON, deletion it's O1, and this one's also O1. The next one is a stack. So is a dynamic data structure, which means it can increase in size, in which insertion of a new element and deletion of an existing element is allowed to be done only at one end. And it's actually a LIFO data structure, which means that the last thing that you put in is the first thing that comes out. So an example of that could be, you know those tubes that have tennis balls, right? That's basically a stack, right? You put in a tennis ball, and the last one you put in is the first one you take out. And the tennis balls keep getting pushed in deeper and deeper the more that you the more that you put in. So some important methods for stacks are empty, peek, pop, push, and search. So empty obviously tests that the stack is empty. Peek looks at the object at the top of the stack without removing it from the stack. And pop removes the object at the top of the stack and returns that object as a value of a function. So if we had put, say we have a stack of languages, and the last language I put in was Java, and I did language.pop, it would return Java. So pushes an item into the top of the stack. So if we wanted to do language.push Java, now Java would be at the top of the stack. Now we have search. So this one returns the one base position where an object is on this stack. So we say search Java, and depending on the size, it might say 1, 2, or 3, or whatever really, or basically the number item that it was in the stack. So here we have some example code. So we're creating a stack of type integers. So that means it can only accept numbers. And now we have we have a boolean which is true or false, and we're checking if the stack is empty. Now it'll return true if it is and false if it isn't. So here we're saying we're printing out the value. So we'll see if is the stack empty, and because we haven't actually filled anything inside of the stack, it'll say false. Now what we're doing is pushing in these values 60, 70, 80. Now we want to print them, right? Because you're seeing here that they're referencing that. So it'll print out stack, it'll print out this stack, and then it'll do comma 60, parentheses 60, comma 70, comma 80. And then this one, stack peek, will print out 60, but it won't remove it from the list. This one, however, will this one actually will, I apologize, this one will return 80 because that was the last one that we put in. The pop will actually also return 80, but it won't leave it there. It'll take it out. So this actually gets rid of the 80, and then when we do stack pop again, we remove the 70, and then this line of code runs, and then our last value pops, and that is current top, and it'll say 60. And this one will obviously print 80 because it was referencing this int x. So here are the big O notation for the stack. So the first one is access, search, insertion, and deletion. So obviously accessing a certain element kind of varies with the size of the stack. Searching also varies with the size of the stack, while insertion and deletion, because you only have at push and pop, and it only works on the first one, that's why it's only O1. Mind you, I'm going to think about these first 4 values. You can ignore these ones because those ones are about space complexity. Next one is a queue. So obviously you guys know what a queue is. A queue is like waiting in line. And This is a dynamic data structure that follows the first in, first out. So whatever you put in first is what comes out first when you want to access a value inside of the data structure. So the queue actually has two ends, named the front end and the rear end. In a queue, insertion can be done at the rear end and deletion can be done at the front end. So here we add our values and then here we delete our values. So you can't go one by one and try to delete certain values. You can only delete the values that is right here. So some important methods are add, which inserts the specified element into the queue, um, element which retrieves but does not remove the head of the queue. So that's whatever's at the end. Offer, which inserts the specified element into the queue if it is possible to do so without violating capacity restrictions. So if it's not too big. Peek, which retrieves but does not remove the head of the queue. And pull, which retrieves and removes the head of the queue or returns null if the queue is empty. Remove obviously retrieves and removes the head of the queue. So kind of this is the same thing as pull, but pull actually returns a value like an integer or a name, a string. So here we have some example code. So here I've created a queue of type string, which means it'll only have basically anything in quotes, right? So words and things of the sort. So we do the first thing, we do queue.pull. Obviously it doesn't return anything because our queue is empty. I didn't put anything in it yet. And it returns null. Now we're going to add banana, apple, and cherry. And we're going to do q plus q. And that's going to print out parentheses, banana, comma, apple, comma, cherry, parentheses. So now we have q peek, right? And since this is not pull, it doesn't take it out. So q peek will always be the first one. So what was the first one? That was banana. So this line will print out banana. Next we're setting string s to q.pull. Now, now this will set string s equal to banana, but it'll also delete banana, so it's not there anymore. And now we do this again, q pull, and that will delete apple. And then we do it again, the current head, and that will delete cherry, right? So now we have system out.println s and then plus s. And what was s? S was actually the first item that we deleted, which just so happened to be banana. Now here are the access, search, insertion, and deletion. Big notation. Let me go through again. Access, search, insertion, and deletion. Big notation for a queue. Now obviously insertion and deletion, right? Because we do it from the ends, it's always the same amount of time, always the same spot that has to be done at. Now accessing and searching, that takes time because you actually have to loop through each value in the queue to find certain things, to access them and search them. Now we have nonlinear data structures. So nonlinear data structures are ones that where the elements are not arranged in linear or sequential order. So basically the order that you actually put them in. So now they're just arranged randomly. So the first one that we're going to look at is a set. Now a set is a special data structure because you can mainly use it to do because you cannot duplicate values. It is it's very useful because when we want to store unique elements, for example, unique IDs. Now, this could be, say, an email or a social security number. That's why this type of thing is very important. And there are many implementations, and the word implementations in Java actually means versions. So there's many different versions of sets, like hash set, tree set, and linked hash set, which is provided by the Java Collection API, which means that they've actually created all the methods for it. You don't have to worry about anything. Obviously, if we had more time, I'd go into depth about all of them, but we don't. So next, we're going down to important methods. So obviously, there are more methods but these are the ones that are common in all of the different types of sets, so all of the versions of sets. So we have add, clear, and contains. So adds obviously adds the specified element to the set if it's not already present. So as we said, it only accepts unique items, so no duplicates. Clear removes all the elements from the set, which is important if you want to reuse your set for different pieces of data. And then we have contains. So this is important if you want to search through your data to find a certain value. So say you want to find a certain email and whatever's associated with that, you can do that. And then we have remove. So this removes the specified element from the set if it is present. So here's some example code, and here we have a hash set, which is a version of set. Now you can see that our set is accepting values called strings, and strings basically just mean words, whatever is in between commas. I mean, not commas, these. So first thing we're going to do is that we're going to use the add method, and we're going to add these elements to the set. So we have geeks for geeks example set, and now we want to print it out. It might do for geeks set example, or it could do example set for geeks, because obviously, as we said, it doesn't actually remember the order. It just puts things around randomly. So here's a big notation for certain algorithms when it comes to certain different types of sets. So we have add, contains, and next. Obviously, for adds, we have O1, which means it always takes the same amount of time to add an element because it always gets added to the same place. And it's kind of the same for all of them. And then we have contains. Some of them are always constant because they're always constant. And then some of them vary with the size of the set. And then these ones you don't have to really worry about. Mainly it's just add and contains. The next section that we have is maps. So a map contains values on the basis of a key and a value. So it's a key value pair. So an example of that could be your name and your email. The name could be the key and the value could be your email. So if somebody wanted to get your email, all they would have to do is parse in your name, and that would return your email. So each key and value pair is known as an entry. So your name and your email is called an entry. I mean, that's an example, obviously, but it's a key and a value pair. So a map contains only unique keys, right? So as I said, your name was the key, which means we can't have two Arshes. We can only have one Arsh. Now we could have Arsh, Mehar, and Dhruv, but no Arsh, Mehar. So a map is particularly useful if you have to search, update, or delete elements on the basis of a key. So say I wanted to get rid of all the data relating to Arsh. I'd have to just search up Arsh in my map, and then I delete everything that's related to it. So that probably to be the email, but it also could be um, your phone number, your address, your social security number, anything like that, basically. And here's an important list where we talk about how all the different maps are related. So some of them are interfaces, some of them are classes, and some of them implement and extend them. So some important methods in maps are clear, put, remove, and get. So clear removes all the mappings from the map, and put associates a specified value with a specified key in this map. So if you want to put put k key k key v value. So if you want to, so an example of that could be put arsh and then my email here, right? So what we're doing is we're putting in an entry. So now it associates my email with my name. Remove. So removes the mapping for a key from the map if it is present. So for security, obviously you need to mention both things. So if you want to remove my entry where it has my name and my email, you would do e.remove arsh and my email. Another important method is get. So this returns the value to which the specified key is mapped or null, if this map contains no mapping for the key. So we have our map with Arsh and Mehar, right? And we have their emails attached. If we want to do e.get Arsh, it would return my email. But if we did e.get Dhruv, Dhruv's name is not on the map, so it would only return null because there's nothing associated with it. So here's some example code. So we're making a map where it contains a string for the key and an integer for the value. So we're going to add in some vehicles, right? So now we have a BMW. It's 5. I don't really know what the number means, but it's just 5. We have Mercedes, which is 3. Audi, which is 4. Ford, which is 10. And what we're doing is we're inputting entries into our map. And this is the key and this is the value. So what we're doing here is printing out the total, the size of the actual map. So it'll be 1, 2, 3, 4. Size will be 4. Now, iterating for these dynamic data structures is actually kind of special, where you have to do it with a for. Actually, it's not very special. You use a for each loop to iterate through each of the values. So we have our string key, and we have the vehicles.key set, and that's basically a value of all the keys in the map. So that would be BMW, Mercedes, Audi, and Ford. And it would print out the key and then the value, right? So it'd do BMW 5, Mercedes 3, Audi 4, Ford, and 10. Now this line you can just ignore. That adds a line in between code. And now we want to find certain value. So we have string search key equals Audi. So we want to find the Audi entry. Now we're going to use our method contains key. And right here, it will say, it'll find where it is, and then it'll display the value, and it'll display Audi. This one basically clears the map, so now we have nothing in there. It's just empty. And then we're going to print out the vehicle size after we've cleared it, and that should return 0. I mean, it'll print out 0 in your console. So here are the important big notations for the map. So we have get contains key and next. So you can see for a lot of them that it's just o dot o parentheses 1, which means it takes a constant amount of time. Some of them it's o log n, which means that the time it takes it gets less and in relation to the size of the data. Moving on. That was actually our last data structure. Obviously, there's a lot more, but if you want to go in more in depth, I recommend a lot. There's a lot of good YouTube videos, but these are just the basics. So the next thing we're going to look at is algorithms. So we have depth first traversal. Now, what we have right here is actually a graph, right? So it's actually a hierarchical data structure, and what that means is that there's a hierarchy. So you see that there's values down here, values here, values here, and values here. Basically, there's values above and below. And if we wanted to kind of make a copy or collect, values from a graph, this is one way to do it. It's actually an algorithm. So depth first traversal means that you go, you start at the root node and explore as far as possible along each branch before backtracking. So you go here, here, here. These are actually called branches, and each small circle is called a node. So we go down here, we go down here, we go down here, then we go back, we go here, we go here, we go here, but then we go back, we go here, we go back, go here, and go here. And might be asking, why do we know to go back here? Well, that's because all of these have already been explored. The next algorithm we have is breadth first traversal, also called the BFS. So BFS is an algorithm for searching a tree data structure for each node that satisfies a given property. And it starts the tree root. This is actually called the root because it's at the top, and explores all the nodes. These are called nodes at the present depth prior to moving on to the nodes at the next step level. So this is the first level, second level, third level, fourth level, and it goes this way. So left to right. And if time persists, we can do exercises, but actually, yeah, let's do some exercises. So if you wanted to kind of see how these things can be useful in the real world, Code Wars is kind of like an example of what they might ask you at interviews. So um, why it's so important is because when they're asking you to solve problems, when they're interviewing you, they're asking you to solve these problems, right? And usually they use lead code. Now, Code Wars is kind of like lead codes where they have these problems online that you can solve, and a lot of these problems actually have solutions that are that use data structures. So I'm going to show you my solution using one of them. So the first thing we're going to do is uh, apologies, I haven't used this in a long time. Well, since high school ended, obviously. All right. Mind you, I've already completed this before, but I'm going to do it again. So train again. So usually these type of problems, they give you some instructions, and sometimes they don't give enough information. That's why it can be kind of hard, right? So here it says, "Welcome, young Jedi. In this kata, you must create a function that takes the amount of U.S. currency in cents and returns a dictionary says hash, which shows the last amount of coins used to make up that amount. The only coin options in this exercise are pennies, nickels, dimes, and quarters. Therefore, the dictionary should return exactly 4 key value pairs." Now you can see it said key value. Now, what does that mean? It means we need to use a map. And that kind of was your clue that you needed to use that. So here, you see these are actually the test cases, right? And this is what your code will be uh, getting inputted in. We'll have inputted in. So one second, let me just think about this problem. Okay, so I was thinking that maybe we should use a while loop. And basically what a while loop does is that it continues doing whatever is inside of it as long as a certain thing is held true. So I was thinking, we have a Boolean, which is true or false, called continue count. And we set it to true. What this means is that it automatically starts counting things. And our while loop will run on the basis of continue count being true. I'm just trying to format this so it looks nice. And the next thing to do is to look at the basis of each value. So we need to have statements that run code and look at certain values. So we need to have ones for 25 cents, 10 cents, 5 cents, and 1 cent. Now you might be asking, how do I do that? Now, if you wanted to get the denomination of like say $1.10, right? First thing you would do is you would take out 25 cents, take out 25 again, take out 25 again, take out 25 again, and now you have 10 cents left. Now it's not more than 25, but it's not, but it's equal or more than 10. So now you know that you have to take out 10. So what this basically means is if cents, which is the value obviously that's coming inside the method, is greater than or equal to greater than or equal to 25, then apologies, this is I've never talked for this long. So then we would put map.put quarters and map.get quarters plus 1. Now you might be asking, why am I doing map.get quarters plus 1 when I just put in 25? Well, you are right, but one thing you might have to consider is that there can actually that this could not be the first time we're running this. It could be the second time, right? In which case we already have a value. Now, if we just did quarters of 25 and we already have 25, then it would just become 25 again. It wouldn't become 50. So it basically gets the value and then adds 1 to it. And the next thing that we have to do is we have to do cents equals cents minus equals, sorry, this is a new keyboard. And what that does is that takes out 25 cents from what's already there. Now, say we have 15 cents. Well, then we can't use 25 cents. We have to use whatever's the next denomination, which is a dime. So 10 cents. So we would do if cents is greater than or equal to 10, we would kind of write the exact same code. So, obviously you don't need to rewrite it yourself. You can just copy and paste and then change it around a little bit. So instead of quarters, we have dimes. And we have dimes again. And instead, we're taking out 10. Now, there are actually two more denominations. And that basically just means we need to copy and paste and choose a few more values. So those denominations are 5 cents, which is the nickel, and a penny, which is 1. So 5 and 1. And I need to change it to nickels, and make sure to do -5, and here to do -1, and we have pennies. So let me just do a quick recap. What we have here is that we're using a map, which has a key and a value pair. Now, the key is actually the denomination of change. So that could be either a quarter, a dime, a nickel, and a penny. And the value is how many of those denominations are inside of a certain amount. So say you have say you have $1.10, right? One key value pair would be quarters 4, because 4 quarters go in there. And then another one would be dimes 1, because once you take those 4 quarters away, you have 10 cents left. And that's dimes 1, because there's only one dime. And if none of these are true, we have to do just in case. So it keeps on going. I mean, and this else statement here is that if there's nothing left, right? If there's something greater than 1, if there's something greater than 1, then it's 0, right? So that would mean continue count is false, which means that this while loop would stop, and it would stop adding values, and it would stop minusing from cent. And we can run this code because I've done this before. So let's test it, see if it works. Oh, one thing that happens sometimes is that you can actually spell things wrong. So I did cents. It's actually cent. And run this again and test it out. See, and it works, right? So our sample test, well, it might not tell us, but here what it's doing is that it's, okay, so here where it's going right now, this example right here, it's giving us 29 cents, right? So if you run through this code, what you get is this equal to 1 quarter. So 29 minus 25 is 4, and 4 pennies, which makes sense. Now this right here is the most important thing, because it gets the previous value and adds 1 to it. And if you didn't do that, it would just be 1, 1, 1, 1, 1. No 4 pennies, just 1 penny. Now we'll try to attempt it, and this is the actual, this is the one where you don't actually see the cases that they give you. This one is a hard one. Now you can see that I've actually gotten it right, so that's good. And this is basically implementation of a map. And you can even see that they actually gave it to you. So here's your hash map. So submit. And if you ever want to look at Code Wars, they have these problems. And obviously, when you finish them, you can look at other solutions. And some of these solutions are a lot better, obviously, than mine. You see, this one is only a few lines. And yeah, a lot of them are actually only a few lines, but mine was just the one that made more sense logically to me. Um, anyways, I think that actually wraps up our presentation. So thank you all very much. I hope you guys actually hope you guys enjoyed my presentation. I know sometimes it can be kind of confusing learning how to code in data structures, but this really is here to give you kind of a base level understanding of how to code. So this kind of lets you, this kind of inspires you and kind of helps you grow on your own. Anyways, yeah, High School Navigator. Thank you all very much. I hope you had a great day, and I'll see you next time. So goodbye, everybody. You guys can start leaving, and I'll. Oh, somebody actually asked a question. Oh, yeah. Thank you, everybody. See you guys later.